Thank you, thank you. I'm Mahak, and I'm here with Akaash, and we are going to present a very critical aspect of distributed systems, disaster recovery. It must have kept many engineers awake at night, when production systems fail, things are not coming back up, customer is angry, stuff like that. So, yeah, we are presenting disaster recovery. What do you think, Akash? If this presentation turns out to be a disaster, do you have any backups?
Well, I have thought about it kind of thoroughly. Since we are two people, in case any of us fails, the other one can back it up. And also, we have like the sheets of paper we have written the things in case it's out of memory. So yeah.
So, let me start with sharing a bit about my background. So, I started my journey with Samsung Research back in India. I was a software engineer there. I worked as a backend engineer mainly, just got exposure to distributed systems. We were making tools in-house for Samsung internal teams. And yeah, then I felt like, I want to study more. So I came here to US. I pursued my master's from Columbia. My main focus there was machine learning and AI. But somehow I got more attracted towards distributed systems, large applications. So after that, I joined Salesforce as their senior member of technical staff. I was working on building their data pipeline, adding new features to it, maintaining it, basically working on the MuleSoft division, if anybody knows about MuleSoft. And then now I'm with Splunk. I'm working for their distributed search infrastructure, specifically Federated Search. So, yeah.
Hello? Yeah. So unlike Mahak's curvy trajectory, my trajectory has been straightforward. I did my education from India till my BTech, and then I joined NC State University. I did my master's from there. While working at NC State, studying my master's, I was also working part-time at the Center of Integrated Pest Management, where I was a part-time data analyst. And during the summer of 2019, I worked in the Google advertisement team as an intern, doing research related to slot placement. And after that, I moved into Amazon. I was a software developer there, also in a distributed system, trying to test out the infrastructure stuff. And then in the summer of 2021, I moved into Splunk, where I also manage a distributed system where we ingest logs in real time and try to find any anomalies there, something like unusual file downloads.
Okay, so let me start this presentation with a very important terminology that we need to know, which is BCDR, which is business continuity and disaster recovery. It's just the set of processes and strategies, that an organization should adhere to so that their critical functions are still running in case of any disaster or any major disruption. So
think of disaster recovery towards IT equivalent of an umbrella. So in case it rains, you are still glad that you have the umbrella in case something is wrong. So in today's data-intensive world, it is practically impossible to just vertically scale the infrastructure because there are memory and other requirements. And so you need to horizontally scale the infrastructure. And in case you horizontally scale the infrastructure, working with distributed systems has its own challenges, and you cannot plan for every unforeseen circumstance that could happen there. And disaster could be of various types. It could be like a DDoS attack happening in your system. It could be a natural flood or there could be power failures, hardware failures, any such. So think of disaster recovery in terms of trying to be prepared for the disaster, responding properly, and recovery. And disaster recovery is the process of actually preparing for the disaster, and a disaster is nothing but something that prevents the system from fulfilling the primary objective. And BCDR is like the overall lifeboat strategy, and disaster recovery is like the boat that powers the boat.
Yeah, engine that powers that lifeboat.
And why is disaster recovery important? It is because that in terms of like critical infrastructure such as payment, a downtime of even minutes could cause millions in lost revenue, and hence every organization should have all these documents. And also in certain European countries, even the vendors of the companies that work with should have these frameworks, because you have a legal framework that you need to adhere in case you need to do business with them. And customer trust takes long to build, and it takes minutes to erode, and hence having a system that can quickly restore is of crucial importance.
So going towards designing a disaster recovery system, there are basically two metrics that we need to focus on. One is RPO, which is recovery point objective, and other is RTO, which is recovery time objective. So RPO, basically it just answers one typical question: how much data can you afford to lose? Technically speaking, maximum acceptable amount of time since the last data recovery point. Telling it with an example, say you are running a financial trading platform. If your RPO is 1 hour, you're basically saying it's acceptable to lose 1 hour's worth of trading data. Is that acceptable? I don't think so. Probably minutes, not even minutes, seconds or microseconds. So that's not a good RPO for a financial trading platform. So that's how we define RPO. But there's a catch. As and when your RPO becomes stricter, the cost of implementing that kind of RPO becomes exponentially high. Similar to RPO, there is RTO. While RPO focuses on data loss, RTO answers a different question: how quickly must you recover? It's the maximum acceptable delay between the interruption of service and the restoration of service. Using our trading platform again, if your RTO is 4 hours, that means your trading system must be back online within 4 hours. Again, that is too much, right? So there are 3 strategies that we need to focus on when designing a disaster recovery system: redundancy, replication, and failover. Let's talk about them one by one. So talking about redundancy, we have 2 types of redundancy. One is data redundancy and the other is service redundancy. Consider redundancy as like an insurance, right? If something fails, you have something else to take care of it. So for data redundancy, we need to first figure out what is the most important data for us. We need to shift our focus towards that data itself, right? Other thing we can do is we can implement RAID configurations. And RAID is not just like a backup, right? It's like it's preventing you from any sort of hardware failures. You have a backup there. The third point is geographically distributing the data. You cannot keep all your data in the same availability zone. If we say in terms of AWS, you need to have your data spread across multiple zones, so that if at all one zone fails, you have data in other zones, so that not all of your data is lost, right? Scheduling regular backups. And apart from regular backups, you also need to test those backups. A backup that is not tested is almost equivalent to having no backup at all. Then again, we can use cloud storage for some kind of offsite redundancy. Regarding service redundancy, similar to data, you need to identify what all are the services that absolutely can never go down. Then again, geographically distributing those services, implementing load balancing. Load balancing is not just distributing the request, but also redirecting it in case of failures, automatic failures, monitoring the health of service. You should know before that something is wrong, before the customer knows it, right? And then, of course, regularly testing the redundant systems.
So the second strategy for being prepared for disasters is replication. Replication essentially means that you have identical copies of the data. The way you can achieve replication can be classified into both synchronous or asynchronous and single master versus multi-master. So what happens in asynchronous mode is that you are copying the data after some time and you are aiming for an eventual consistency mode. So essentially, subsequent writes and reads after that might generate different results, but over time, the results are going to be same. And in case of synchronous replication, you are having some sort of like a locking mechanism, or you are preventing any more reads or writes so that you are able to have the same data in all the replica nodes. So if you have like a synchronous replication mechanism, this is kind of crucial for applications such as a banking application, and you can have like an asynchronous replication where you have a system such as Instagram feed, so that even the data is incoherent for some time, it's still fine. And if you are having a synchronous replication, it means you are not optimizing for like the writes and reads that can happen to the system, and you are only caring about the data consistency, and hence it's going to take impact on the performance. Whereas in case of asynchronous replication, it's going to be a fast performance system, but with data consistency issues in near time. And the second way that we can classify this is using a single master or a multi-master. So in case of single master, all the operations are happening on one of the server nodes, and that's the only point of contact for coordinating, getting all the read and the write request, and then passing it to all the replica nodes in through either synchronous or asynchronous mode. Whereas in multi-master, you are having two identical master nodes, both ideally able to accommodate both the read and the write request. And in case of multi-master, you would need probably a consensus algorithm and not so easy architectures of maintaining it, and it requires conflict resolution in case the data is sort of different in both the master nodes or any of the replica nodes. Whereas in single master, it's quite simple to accommodate. It requires no conflict resolution, it requires no consensus algorithms, and the only gotcha is that the write throughput is going to be constrained in such circumstance. Whereas in multi-master, you have essentially vertically scaled the system, and you are able to accommodate much more write and read requests through the multi-master. And while we have planned for any disasters that could happen, but still sometimes disasters do strike, often in unplanned ways, and a failover for a disaster recovery system is the secondary system that takes by when the primary system sort of fails. And this can also be classified into two ways, whether the failover is happening automatically via code, via the load balancer using like nginx or some other reverse proxy or different methods, or whether it's happening via a privilege execution via code by a software engineer, by a on-call, by a privileged user. And if we dive deep into automatic failover, it can still be classified into two more ways, whether there's a secondary system takes time for the, so what happens in active passive mode is that there's a primary server and there's a secondary server. And only the primary server is accommodating the read and the write request, where the secondary server is in standby mode. And when the primary server goes down, depending on the time it takes for the secondary server to be booted up and running, it can still be classified into warm and cold restarts. In case of warm restarts, it means that the secondary server has the most up-to-date data, and it just requires like a small amount of time to get the diff of the data. And in case of cold restarts, it means that the secondary doesn't have so much data and it requires significant amount of time to be up and operational. And in case of active failovers, it means that there are essentially two master nodes that are running in real time, and you have essentially used 2x capacity to be entertaining all the read and the write requests. This is kind of the best architecture in my opinion, because it doesn't have any customer impact, but the cost is the only concern, because you literally need to 2x the cost of every resource that you probably need. And some of the best practices for automatic failover is that you need to probably test quite a lot. You need to run various simulations. A good example for this is the Netflix Chaos Monkey. So what Netflix essentially does, it uses an internal tool that breaks the communication between different microservices, and then it tries to find out whether systems are running healthy in case any upstream or downstream components are out of the way. This is a great way to identify any bugs in your system, whether your systems are up and running in real time. And since this is an automated system, we need to be very careful about the false positive, false negatives, and hence monitoring and alerting is of crucial importance. So whenever an automatic failover is happening, it should probably ping the on-call, and there should be a run book where the on-call needs to see what needs to be done. And whenever these steps happen, we need to also update the documentation so that any future engineers or management can look and see and run dashboards to see how the system is performing in real time. And the second failover is probably not so good. That's the manual failover. So this is, for some applications, automatic failover is not really possible. So in that case, the best practices to follow is to perform the pre-failover checks, checking if the system is indeed down, checking if the system can be up and running using the manual steps that you can take. And similar to the automatic failover, the on-call or whoever is the privileged user should be monitoring the dashboards, and whenever the instructions to boot up the secondary system has been completed successfully, they should also be checking if the system is moving towards a healthy state. And documentation updates is also of major importance in this field. And so a recap of the failover mechanisms, it could be classified into manual and automatic. In case of automatic, you have active passive mode, where there is a backup node that is ready to be up whenever the primary node goes up. Depending on the time it takes, if it takes longer, it's a cold restart. If it's faster, it's a warm restart. And in active mode, it's basically that there are two nodes running independently and serving traffic real time.
So now all these concepts we have put together in a form of a demo, a small demo. So this image shows the architecture of that demo. So we have multiple components here, right? So the first one is client. For now, I'll assume the client is just me sending up curl requests to a server. In front of our servers, we have an Nginx reverse proxy, acting as a reverse proxy. Also, we are collecting some kind of metrics and logs from our servers using Prometheus, which is then powering our Grafana dashboards. Again, for our Nginx reverse proxy, we have Nginx exporter that is helping us to gather those metrics. So I'll talk about, I'll show you the code a little bit so that we have a good sense of what we are running. So this is we are actually using Docker, and we are spinning up multiple containers which are handling these components. So as you can see, for now I'll just comment out the client. This is what Akaash will use later on. So we have a primary server. Let me stop it once. Okay, yeah. We have a primary server. We have a backup server that we talked about. We have a load balancer, which is Nginx. Then we have Prometheus, Grafana, and Nginx exporter here. So these are all the 6 containers that we have. So let's try and run these. So I have a small utility script that actually starts these containers. And let's just go and look at our Docker desktop and see that we have, okay, so we have these containers up and running. So let's see how a happy path will look like when everything is working fine, right? So this is the happy path. So the client sends a request. Nginx, acting as a reverse proxy, will route this request to our primary server. So for our demo purpose, we haven't put an external DB. We are using my laptop's file system as a DB per se. So the Nginx will route the request to the primary server, and the primary server, it's up and running, will respond, and that response will be sent back to the client. Very, very happy and easy path, right? One more thing which will happen in this happy path is to be prepared for any kind of disaster. And as a part of preparation, there is synchronous replication that is happening between the primary server and the secondary server. So let's see how all of it is happening. So this is, let me open a new client. Okay, so let's start with, so we have actually multiple endpoints in our server, right? So we have endpoint for health, we have endpoint for metrics, we have some other health points for checkpointing and stuff, which Akaash will talk about. Yeah, so let's first check the health endpoint. So we are sending this request to localhost. One second.
It's in the README.
Yeah, 1 second. Yeah. So we are sending the request to port 8080, which is nothing but Nginx is actually going to get this request, and it's then going to route it to primary server. So we got a response from the primary server saying that the status is healthy. Now let's try and maybe send a request with some data, some like let's say key value pairs, right? So let's say we sent a curl request to Nginx saying that I want to put a key value pair test1 before failure. So I got the response from primary that it was a success. Now just to make sure that we got the data is actually in my file system. I can see that data.json got what I sent, and in fact it is creating a backup also in the backup system. So we are actually synchronously replicating the data in both, like the primary is actually replicating the data inside the backup server. Just to make sure we can even read it. So we have the data. Now this is a very simple happy path. Now Akaash will come in and create some chaos here.
Yeah, so what essentially we have done for demo purposes is to make the primary server unhealthy. So the load balancer is continuously looking into the health of the server, and in case anything is wrong with the health, it automatically redirects the request to the secondary server. So what happens now is that the primary server is not there anymore. It's not responding. It's sending 503 errors. And so internally, the Nginx reverse proxy is going to redirect the request to the secondary server and respond if it has got the requisite data into the client. So this is just a checkpoint that this is just a request that we have made so that internally it's going to toggle the status of the DB to be unhealthy. So if we do this, the database failure has been simulated.
So now our primary server, if we send a request to the primary server, for all the requests, it's going to give 500 internal error or a 503. So our primary is no more working.
And now if we check the status of the load balancer, so notice over here that the role has been picked up by the backup server. And if we go a little above, when Mahak first called the health endpoint of the load balancer, it was being responded by the primary, and now it's being responded by the backup server. And let's try to try to first read the data.
Read the previous data that I wrote when the system was healthy.
Yeah. So if we first read, one second. So if first read the data, it's still able to give the proper response along with the correct data. And then we'll try to write in real time when the primary server is unhealthy. Let's try to do that. So if we see over here, now the test2 data is only written in the backup node, and now in the primary server, the data is no longer there because the primary is unhealthy now. And we try to test any read requests for the test2 data. We are able to get the proper key value pairs. We also try to read the first data again. It should be able to do that. And then we are triggering a system recovery. So when the system is getting recovered, we are essentially getting all the data from the backup node. For the purposes of this demo, we have assumed that the backup server will not go down, but in real world scenario, we'll have multiple as such replica nodes. And then when we call the primary health endpoint, it's being responded by the primary node. And we try to write so let's check. So once we have recovered from the disaster, the data that was there in the backup node has been also replicated in the primary node so that it has the true context of the world now. And now if we call the health endpoint, since the primary is healthy, it's being responded by the primary saying that it's healthy now. And if we write the third data over here, it's a success, and the data should be present both in the primary node and also the backup node. And similar results can also be found if we just use the curled endpoints. So what Mahak essentially did was to create a manual client, and we are just interacting with the load balancer. So what we could do this is we could create a client that could automatically send in multiple requests in real time, and also intermittently we could toggle the status of the server to be healthy, unhealthy, and see whether the system is able to be performant in real time. So what we'll do now is we are going to stop the existing containers. and we are going to uncomment the client. It's gonna take about 30 more seconds for this to solve. Yeah. So what essentially is the client doing is it's sending data to the load balancers. It is generating a random key value pair and automatically sending the data. It's in a while loop. And also intermittently, we are also toggling the status, the health endpoint to be healthy and unhealthy. And then we are going to simulate this. So I think we have simulated this. So if we look over here, that the client is now automatically sending data, the key value pairs, and we are getting success primary. And this is going to happen for some time. And after some time, you can see that we have toggled the failure status in the primary server, and now all the requests are getting routed to the secondary server, and it's been written by the backup server. And if we go over here, and also we have toggled the health endpoint to be healthy, and now all the requests are getting routed to the primary server. If you look also at like the backup data and also the primary data, we see that the key value pairs are getting generated successfully now. So for this purposes of this video, what we have done is we have copied all the data from the secondary node to the primary node, but that's not a good thing that we should do. So also for this demo, we have also introduced checkpoints. So checkpoints are happening both in the primary server and the secondary server every 30 seconds, more or less, for this demo. And it's checkpointing the data that's present at that instance of time. And the checkpoint ID is the hash of the data that's being present. So now if we So this is the list of checkpoints that's available. So you see that the number of keys are continuously rising, and this checkpoint is happening in both the primary and the secondary servers independently. So primary is running at port 5002 and secondary is running at port 5003. Since there is a lot more data in secondary, the number of keys have been increasing gradually. And also both for real world use cases and also for like when you are creating systems manually, because of the size of the data in the checkpoints continually increasing, we should also clear out the checkpoints. So also for this demo purposes, we are only having the past 5 checkpoints. And we can even look into one of the checkpoints, let's say. So how does the data look like? So if we do, let's do a JQ. So this is what a checkpoint looks like. We hash the data. The data has like the key value pairs along with the metadata such as like the hash, the time it took, and the number of keys. And I think Mahak can show the remaining.
Yeah. So I think one of the best practice in these kind of systems is to have monitoring dashboards that we talked about, Prometheus and Grafana. So we have configured those also for the purpose of this demo. So let's have a look at Prometheus first. So in the code itself, in the server code, we actually had configured metrics. For example, checkpoint counter, health status, response time, requests. So now we can actually see those metrics here. these are all the metrics, and this nginx underscore metrics are the ones that are being created by nginx exporter. We can, if you want to figure out what is happening with your system, you can actually do some kind of queries here. I think for Prometheus we have promquel. So let me try and do a query here. So yeah, this query is actually showing how many requests each of the server got till now. So primary server got around 417, backup server got around 214. This is probably because of the client, because it's continuously sending the requests, failing it, recovering it. So these are the number of requests till now that we got. We can actually make it more fine-grained, and let's make it method-wise as well. So primary server got 213 GET requests till now. So this way you can actually monitor what is happening with the server, and based on, like, this is the raw data, right? You can actually create graphs out of it, visualization out of it. So for that we have Grafana configured. I just have admin for now.
That's the default.
So these are the small charts that we have configured. I think after some time you will see the primary server going down because the client is running, I suppose. Is it? Yeah, the client will be, making it unhealthy. So probably in 30 seconds or so this should go. Okay, it went 0, right? Because the client is running, it's simulating failures as well. So based on these charts, you can actually configure some kind of alarms that can ping the on-call engineer in the company, and they can then start working on it and check what is happening. Again, we have configured this chart. We have configured to figure out what all endpoints are being hit and what's the status they are returning and stuff like that. Also, we have metrics. Let me go to home. Yeah. So these are all the kind of charts that you can see. The ones that are nginx underscores are automatically getting created by the nginx exporter. And you can look into these, figure out what actually they are trying to denote. So yeah, I think that's all we had for the demo. And let's go back to the slides.
And we actually made it kind of open source, I think. Can you show the...
Yeah, I'm looking for the slides. They're gone. Yeah, it's here. Okay. Yeah, so this whole demo is actually in my repo. We have made it public. And if you have any more questions, you can ask now. You can also reach out to us on LinkedIn. So, yeah.
Two things. I was working on a project that we started, and we planned to do the disaster recovery after 3 days. So we worked for 3 days, we shut it down, and we turned it back on, and we tried to turn it back on, we tried to turn it back on. And we used an Oracle database. Oracle had problems, and our procedures weren't right. But that was our planned disaster recovery, and we figured out we couldn't recover. We had to fix that. The other instance, I was at a university, and you're talking about documentation and everything. They had modified some of the shutdown procedures, and we had an air conditioner go bad, start a fire, and release the halon in the data center. Everybody had to leave the data center. The automatic, since they had modified the procedures, the automatic things didn't come up, and this was the first day of the university, and all the students couldn't get into the system. And they spent most of the day fixing it, and I spent part of the night. Once they got things back up, they're trying to get the systems going. But document and check it often and make sure you're when things change, you document.
Yeah, exactly. I think that's what one of the points that I made was testing your backup is really important. If you have a backup, let's say I say I have done all the disaster recovery, but there's nobody who's testing my claim, then it's actually like having a no backup. You don't know it will come up or not, right? Yeah, yeah. That was nice. Yeah.
I was wondering if the CrowdStrike event in July caused a DR event for either of your companies. And
Oh, it did. It did. It was bad. It was bad. I mean, we are here talking about it, but yeah, it still happens. But something is still better than nothing. We still have policies and strategies, backups in place. But yeah, it is what it is. But, yeah.
Was there any, just quick follow-up, any lessons learned from that?
Yeah, so I think when we roll out our systems, we only roll out in a small scale. We try to mitigate the disaster into like proper subset of the nodes that can happen with the change. So the proper way to test is test it small. If it's okay, test it in a larger radius, and then iteratively, in case something is wrong, you reboot and
yeah, one more thing that became very prevalent after that was we started introducing a lot more flags. So, you introduce a feature, you always guard it with a feature flag. And, if at all it's causing any kind of regression, you just have a one fix of just turning it off. You are not impacting the whole system. You don't have to wait for yet another release to fix it, right?
yeah.
Yeah.
Very good. Thank you.
Thank you.
All right. Any more questions?
Any other questions? No, behind me.
Is there ever a risk of introducing too much? In other words, by introducing more controls and monitoring, you actually are introducing more risk into your system by doing so?
It's actually two sides of a coin. You can try to create a simple architecture, hope nothing goes wrong, and it's kind of simple to implement. It's straightforward. You require less resources. But situations, as in like if the traffic burst keeps on increasing, you cannot simply afford to have a simple system. The system is going to be complex because simple systems can't scale so much. And as such, when you have a distributed systems, a lot of things could go wrong, and hence you need backups, secondary servers, replicas, and I think you probably need a disaster recovery strategy if the system is too big. You would need that. You cannot afford not to have that.
Yeah.
Any other questions? I did not see any on Slack, so thank you.
Thank you so much.